In Lecture 18, we're going to begin looking at trigonometric identities. To begin with, we're going to start by just understanding some of the basic manipulations that we can do with algebra to our trigonometric expressions. And then moving on from this lecture, we'll begin looking at how do we prove or establish the truth of an identity. But to talk about identities, we need to begin by defining what we actually mean by that terminology. So let's start by saying two functions, f and g, are said to be identically equal if f of x and g of x are the same for every value of x for which both functions are defined. So this is different than the type of equations that we solved in previous lectures. These are statements that are true no matter what x we plug in. And these are what we call identities. That kind of equation is called an identity. An equation that is not an identity, one that is true for only specific values of the variable and not for every variable, is called a conditional equation. Of course, this is not the first time that we've looked at identities. We have a handful of identities that we've used to solve problems earlier. For example, we have the quotient identities, which tell us that the tangent of an angle is always equal to the sine of that angle over the cosine of that angle, as long as that angle is within the domain of all the functions involved. In this particular case, tangent, you'll remember, is not defined for things like pi over 2 or negative pi over 2, and there's other values, but as long as that angle theta is defined for all the functions involved, we know that this statement is true. And cotangent, similarly, is cosine of theta over sine of theta. Of course, we know that cotangent is also the reciprocal of tangent, which is why that's true, which reminds us of the fact that we also have another group called the reciprocal identities, that cosecant is 1 over cosine, secant is the same thing as, did I say cosine? Cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. And while we are refreshing our memories from old trigonometric identities, let's not forget the Pythagorean identities. Try that again. Pythagorean, which comes from the Pythagorean theorem when applied to points on the unit circle. Sine squared plus cosine squared is always equal to 1 no matter what angle we plug in. And then we were able to, in previous classes, or previous lectures I should say, manipulate that equation into these other two by simply dividing through by cosine squared or sine squared, and they give us tangent squared plus 1 is secant squared, and cotangent squared plus 1 is cosecant squared. We also have our even-odd identities, which simply remind us that certain functions in our list of trig functions are even, and some are odd. The odd functions are the ones that we can pull a negative from inside the argument to outside the function. So sine of negative theta is negative sine of theta. Cosecant of negative theta is negative cosecant of theta, and so forth. And then the two even trig functions are the cosine and the secant function. In many cases, the process of proving a trig identity is going to boil down to doing some algebraic simplification of your trig expressions. And so in this lecture and in the homework for this, we're primarily going to be looking at practicing some of those algebraic manipulations. So in this example, we want to simplify cotangent of theta divided by cosecant of theta. And the hint is to take this function and take all of the expressions that are in the expression that we have and rewrite them in terms of sine and cosine. So cotangent of theta over cosecant of theta could be rewritten in terms of sines and cosines. For example, we know that cotangent of theta is cosine of theta divided by sine of theta, whereas cosecant of theta is 1 divided by the sine of theta. Now we've got a fraction divided by a fraction. We remember from our algebra that to divide fractions is to invert the denominator and multiply. So this becomes cosine of theta over sine of theta times sine of theta over 1, because I'm going to flip that bottom fraction. And now sines cancel, and you're left with cosine of theta over 1, or just cosine of theta. In other words, the cotangent of theta divided by the cosecant of theta will always give me simply the same thing as cosine of theta. We've simplified that expression. In this example, we are asked to show that cosine of theta over 1 plus sine of theta is identically equal to 1 minus sine theta over cosine of theta. That is, we're actually asked to show this identity. And I give you a couple of suggestions here. The first thing I want to point out is actually the second suggestion that I give you here. Well, the strategy for showing something like this is to always start with one side of the identity and then apply some operations that don't change its value. And then we're going to use that use of algebra to turn one side of the equation into the other. So we're going to say start with one side, maybe this side, and try to turn it into the other side. And I've given you a hint here. In fact, what you're going to see in this lecture is several suggestions of operations to try to see if you cannot manipulate one side into the other. In this particular case, I've given the suggestion to take cosine of theta over 1 plus sine of theta and multiply by the conjugate of the denominator. Now by conjugate I simply mean if you've got two terms added together, the conjugate is now to subtract the two. If they were subtracted, it would be to add. And you multiply by, instead of 1 plus sine of theta, 1 minus sine of theta. We do that on top and bottom. Now if you multiply the top, I'm just going to actually leave it in factored form. You got cosine of theta times 1 minus sine of theta. In the denominator, we've got a difference of squares multiplied together. So if I multiply this out, first, outside, inside, last, the first gives me a 1. The outside and the inside end up canceling because you get a negative sine of theta on the outside and a positive sine of theta on the inside. They end up adding to 0. And now sine of theta times a minus sine of theta gives me a minus sine squared of theta. Now the reason why this is now helpful is that if you do 1 minus sine squared of theta, recall that cosine squared of theta plus sine squared of theta is 1. So moving the sine squared to the other side, cosine squared of theta is 1 minus sine squared of theta. So this right here we know is just cosine squared of theta. So you end up with cosine of theta on top times 1 minus sine of theta divided by cosine squared of theta. This cosine cancels with one of the cosines on bottom, and I'm left with 1 minus sine of theta divided by cosine of theta, which is exactly what I was trying to prove. So I'll put a little box at the end. That's the way that we indicate that we've proven or finished showing an identity to be true. Now we have an example again where we want to do some simplifying. This one's not actually showing, this is just simplifying. But to simplify, we need to practice our algebra a little bit here by adding fractions using a common denominator. So when I have 1 plus sine u over sine of u, I'm going to leave a space, and cotangent of u minus cosine of u, right, over cosine of u, I look at this and say, what is the common denominator? What's the lowest common denominator? And since 1 denominator has sine of u and the other has a cosine of u, the product of those two functions is going to be my common denominator. So I look at my first fraction and say, what's missing from that one? Well, it's a cosine. So I'm going to multiply by cosine of u over cosine of u. In the second one, I'm missing sine of u over, or I'm missing a sine of u, so I multiply by sine of u over sine of u. Okay, and now what you've got is that this is now all equal to something over sine u cosine u. If I multiply cosine times 1 plus sine, if I distribute this out, I get cosine of u plus sine of u cosine of u. And now on this one, if I multiply this out, I have plus cotangent of u sine of u minus cosine of u sine of u. Okay, that's equal to this. So now this is still equal to the sine u cosine u occurs positive and negative, so they cancel each other out. And you have cosine of u plus, now cotangent, since everything else is already in sines and cosines, I think it'd be a good idea to change that into cosine of u over sine of u, and that's times sine of u up here on top. And still look over our common denominator, sine of u cosine of u. So the sines will now cancel each other out. And again, all I did was I replaced cotangent of u with cosine of u sine of u. So this gives me a cosine of u plus a cosine of u, which is 2 cosine of u over sine u cosine u. Right, because I just had a cosine here plus a cosine here, which gives me 2 cosines. And now the cosine on bottom cancels with the cosine on top, and this whole expression simplifies into 2 over sine of u. So for any given value of u, this is equal to 2 over sine of u. We were able to simplify it, and again the strategy was, let's find a common denominator and combine those fractions. For our last example in lecture 18, my suggestion is to try factoring. If we can factor these, we may be able to simplify further. In this particular case, what I mean by factoring on the denominator is to pull out the common factor. So if I start with sine squared of v minus 1 over tangent of v sine of v minus tangent of v, I notice in common they have a tangent of v, which I could then factor out, leaving a sine of v and a minus 1. Now on top, what I notice is that this is a perfect square and this is a perfect square, and so I can refer back to my algebra factoring rules for perfect squares, that is a difference of squares, which gives me, if I have something squared minus something squared, that factors into a plus b times a minus b. So what is it that's squared in this case? Well, a is a sine of v and my b is a 1, right? And then I'd have an a squared here and a b squared there. So this means I can factor the numerator into sine of v plus 1 times sine of v minus 1. And the reason why that is so helpful is you notice now sine of v minus 1 appears on top and bottom, and so I have a sine of v plus 1 over tangent of v. And so there's my simplified 4.